Hey guys, Mr. Henderson here. So I taught AP Physics for about 9 years before teaching anatomy and physiology and earth, wind, and fire. And so this comes from when I taught AP Physics and some of the materials that I would have had my students do at the end of the first semester. Now I realize some of you are feeling overwhelmed and stressed because you feel like you didn't learn some of this stuff, but it's totally okay, and we'll get through all this together. But what I thought would be helpful is just running over the questions that I posed so that you can see that it does align with some of the stuff y'all have talked about through your projects and labs and things. So I'll just kind of go through the questions here and show you the answers. That way you can compare against any that you were able to do. And then I'll talk about what your final will kind of look like based on how it feels like y'all are doing so far. So this first question here, you can see a block and a ramp, and anything with an inclined plane is an acceleration question. So you can see here that if we're asking to decrease the acceleration of the ramp, of the block rather, that means we need to somehow either lower the height of the plane, that would give it less potential energy, which means it would convert to less kinetic energy. Or if I lower the angle of the plane, then the component of the gravitational force down the plane is going to be lower. If you didn't learn the equation for all of that, that's totally fine. But if you did learn how to do like a free body diagram, the force holding the thing down, whereas there's a components here and then actually into the plane, which opposes the normal force. I know y'all learned a lot of equations for the different forces. So you'd have Fn and Fg. Down the plane, I would have the parallel component of Fg, whereas into the plane, I would have the perpendicular component. So part of that force is holding it to the plane, part of it's pulling it down the plane, and really any force question can be broken down by a free body diagram, which is what this is. So if you don't know anything about free body diagrams, that would be a great thing to look back at and learn when you're looking at Newton's laws. Number two is a question about a merry-go-round. This is really asking about one of Newton's laws being the equal and opposite reaction force. So if I have a person being held in place, then the same force I'm applying to the merry-go-round is being applied on me. So it says here it would be equal in magnitude and opposite in direction from the frictional force exerted on the merry-go-round by the person. So if those forces weren't balanced, the person would be accelerating either off the merry-go-round or the merry-go-round would be accelerating somehow and speeding up or slowing down in response to the person. I know y'all didn't do much about tension, but all this is asking is as I raise up, it's going to do that click thing every time I start annotating. As I raise this angle up higher or lower, I'm going to be helping the sled, quote unquote, do work. So if here, like if we keep the force constant, but if I half the angle, meaning I pull at a lower force angle, you think about that if I'm pulling my little sled here, and then if I lower it, I get more in line with the motion that's occurring, then obviously the acceleration is going to increase. I'm going to pull it faster and faster, which means that the new normal force would have to be greater, because if I'm lowering my angle here, then this normal force that used to I was helping by pulling upward on, if I lower, I'm doing less, so the normal force has to increase because it's making up for my lacking y component of my force. So if I do less force here in the y direction, then the normal force has to do more because we know there's a set amount of gravitational force holding the sled to the ground. So that's why the new normal force would be greater. If I increase the angle, meaning if I pulled it a higher, then the normal force would decrease because I would be doing more of the work on the sled up opposing FG. So you can see that question kind of either way, and you'll see that more on the practice quiz that I'll be posting. On this one, the tension one, I realize y'all, like I said, didn't do a lot of tension, but all this question really breaks down to is whatever force is down here on this weight has to be balanced by the forces that are up. So if I take the components of the T force here that are upwards, the Y components of T1 and T3 and T2 have to be equal to T1. Otherwise, the mass would be oscillating or moving in some way. Um, Question number 5 is a kinematics problem. If you don't know your kinematic formulas, it's okay because they're on the formula chart, which you should be able to use on any test or quiz. And so when you plug it in with a known distance and a time, and they give you the weight, which is a force, you should be able to do your F equals ma. You find your acceleration first. But here, since it says it's a nice constant force and it's pulled to the top of the well, then you should be able to find that the tension is 24 newtons. If it was initially at rest, you could find the final velocity using the time and the force, and then solve for your force. And I could show that if needed. Number 6 is a little bit longer question. This would be a force question with a free body diagram. By giving us the force BV, and then if you see here the answer is G minus BV over M, all that's doing, we know that the net force is equal to mass times acceleration. So all of my forces, which would be Fg, minus the retarding force, which is just meaning it's slowing it down. That's what we mean here. Means it's opposing, so that's why I have to subtract here. So minus BV would be equal to MA. So that's why ultimately this would be mg minus bv equals ma, which means that if I'm trying to find the acceleration of the ball, I would have a equals mg minus bv over m. And you can see where if I cancel out m here, I have to leave it over bv, so that's why I cancel it here, and then I'm leaving m underneath, so I would have g minus bv over m to find the actual acceleration of the ball as it falls. And I know y'all did a little bit of projectile motion, so that question is totally doable. This one, on the other hand, might not be, because here I have a net force applied by this mass, which would be mg, minus, there's an upward tension here, which is provided by this weight. So this would be 3 mg, and then upwards we would have the normal force. However, since it says they can move without friction, then the only acceleration to the system is caused by this block here, which means mg would be equal to the total mass of the system times the acceleration of the system. So mg would be equal to, if we look at our total mass, we would have m plus 3m times a, which means that if I do 4m a is equal to mg, that's why I get g over 4 is the acceleration of the system. So that's how you would solve any kind of complex block system like that. Let's see, did we skip one? Nope, we're good. Okay, continuing on this, the motion detector, I know you did a lot of velocity time and distance time graphs, so those questions you'll see kind of on the quiz. The reason why we have this nice curve is because obviously the block, or the cart in this case, would be accelerating. So when you see a curve on a position versus time graph, then you would see this nice curve here. So since this one says we're seeing an acceleration and a mass for a constant net force, if I have a constant net force, I have a constant acceleration, which means I'm going to have that curve. Here's a free body diagram showing a person pushing a block against a wall. So if I push into the wall is pushing back on me. That's the normal force here. Up, opposing the gravitational force, would be the force of friction on the wall. Just like if I was leaning on the wall, it's going to try to help me not slide down by opposing it and holding friction up. This one's very similar to the one we did earlier, where you would just look at the total mass of the system and divide out to get the acceleration. Number 11, and I know I'm going kind of fast, sorry, but this is really just for those of you who are interested. This is a question where you're looking at a force over time. And so if I have a block of mass 3 kilograms, which is initially at rest, by applying a force to it, I know I'm going to be doing work, increasing the energy of the system. And so if I do it says the horizontal surface with the force shown at time t, the acceleration of the block at time 2 is equal to how much? So if I go to 2, I would be able to find the force that was applied at 2 seconds. So all we would have to do then, force is equal to mass times acceleration. That's hopefully an equation you all learned, which means that the force, 4 newtons, would be equal to the mass, 3 kilograms, times the acceleration. So if I want to find the acceleration, it would just be 4/3. Okay, hopefully that was one y'all were able to figure out. Now this one is a work problem. So when you're looking at work, we know that's increasing the energy of the system by doing work on the system. Like I think y'all did the stairs lab where you were running up the stairs and doing work on yourselves to increase the gravitational potential. So all of this area here is positive work, whereas this is negative work. And if you notice, this and this match, so those essentially cancel each other. And so all I have is FD. This is F, this is D, so that's the amount of work that's done, force times distance. Here, if my ball starts with 10 joules of energy up here, and it bounces, so after the collision, it bounces back up and it only has 7 joules of energy, then that means when it left the ground, it had to have only had 7 joules, which means it lost 3 joules of energy, lost. Really, where did it go? We know it went to sound, heat when it hit the ground, a little bit of deformation of the ball. Okay, moving right along. I know we're going really, really fast, but this question is about energy. So by looking at the potential energy at point 2 is 0, because that's the max speed of the pendulum. Where the kinetic and potential energies would be the same would actually be up here, kind of closer to point 4, because when you think about energy, if the gravitational potential energy is at a maximum at 0.4, and we know it's 0 at 0.2, and then back up to here at 0.1 for potential UG, your kinetic energy would have to be at a minimum here, at a maximum here, and a minimum here, which means kinetic energy, let's do it in blue, would look something like this, whereas your potential energy would look something like this. So I'm going to exponentially lose potential and gain kinetic, which means at 0.3, I would have roughly equal amounts. And then the speeds is what you would have to look at to find the kinetic energy. Obviously, it's going to be a maximum here and a minimum at 0.1 and 4, which is why they're equal.